galaxies and structure in the universe evolve, so active galactic nuclei evolve as well, and in ways that are actually very interesting. At first, it was hard to figure out how does that happen, because the luminosity function of quasars, at least in its bright end, is well represented as a power law. So if you plot log of the number of quasars per unit volume, unit luminosity versus log of the luminosity, a power law looks like a straight line. Then you can compare luminosity functions at two different redshifts, and you still see a straight line. Now the question is, how did it get to be that way? If the quasar numbers evolve, that means the luminosity function goes up and down. If the luminosities evolve, it goes left to right. But you can't tell without any features. And so for a long time, it wasn't clear whether it was a density evolution or luminosity evolution. All we knew that there were many more quasars at large redshifts than there are here now. That degeneracy was broken once the observations got to be deep enough so we can see that there is actually a feature and luminosity function is not a pure power law. And here it is how it looks like. The truth is the combination of both. There were more quasars back then, but they also tended to be more luminous. And you can think of it as in a sense of, well, there are things back then that aren't here now, but quasars are not so much objects as events, as phases of evolution in general behavior of supermassive black holes. We think that any galaxy with a massive black hole in the middle can go through multiple episodes of quasar-like activity. And so those were more frequent in the past, and they're also more luminous. And so this is now reasonably well understood, and we can integrate the number of quasars at any given redshift and see how that whole thing changes as a function of time. And the result is something like this. As we look from here now and go to higher redshifts, the numbers increase. The comoving number density of quasars over all luminosities goes through a broad maximum around redshifts 2 to 3, and then past about redshift of 4 declines again. Now if you flip this and think in terms of cosmic time, this makes a perfectly good sense. At first there is nothing, you have to start building them up and fueling through, say, merging of galaxies. That activity reaches a peak somewhere between age of universe of 1 and a few gigayears, and that's the peak of the quasar era. And then it declines because the galaxy encounters are not as frequent as the universe expands, and there is less gas to be used to fuel them. So we think we have a reasonably good understanding of the picture. You may recall that history of cosmic star formation is something like that, not exactly the same, but qualitatively very similar. Another way to look at this is through radio sources. Radio sources, we believe, are largely powered by supermassive black holes, but not always. And if you look at the luminosity function of radio sources and then get the redshifts, understand where they are, you find out there are really two components. On the bright end, most of the luminous radio sources are powered by the accretion to supermassive black holes. On the faint end, actually they're dominated by star formation. Star formation can produce radio emission through supernova remnants and such. And so then those two will evolve differently depending on the history of star formation versus history of active nuclei. They're correlated, but not perfectly. And indeed, as far as the active nuclei are concerned in radio, they do evolve very much in the same way as quasars. Since the beginnings of radio astronomy, astronomers counted radio sources as a function of flux. And this was essentially a form of cosmological number density test, but since they evolved rapidly, it was difficult to derive any cosmological conclusions aside from disproving steady-state cosmology. And now this is actually done in detail, but with measuring of redshifts as well. Another question is, are quasars clustered, just like galaxies are clustered? And the answer is yes, obviously it has to be. Not only are they clustering in a similar way as galaxies, or rather groups or faint or small clusters of galaxies. But at very small separations, their clustering is even stronger. And there are many cases of binary quasars known, actually two physical quasars orbiting each other just like binary stars. And their numbers seem to be increasing as the separation gets closer than, say, about 100 kiloparsecs, which is where Galaxian halos just begin to merge. In other words, when galaxy merging really begins. So if the quasars are fueled by galaxy interactions, this is perfectly understandable. There is also a couple of cases of triple quasars known. And if the quasars were following clustering of galaxies exactly, this would be essentially impossible to achieve because quasars are rare. To have two quasars together would be even more rare, have three, even more rare. But if the proximity is correlated with the onset of quasar activity, say because of dissipative merging, then you will see cases like this, and that's exactly what's observed. What about properties of individual quasars? Well, we have their spectra, and as far as we can tell, they do not evolve very much at all, since the highest redshifts, we find them beyond redshift of 6 to the present day. There is change in spectrum due to the intergalactic absorption by hydrogen, as you would recall, but aside from that, as far as we can tell, there is very little evolution, if any. So quasar phenomenon itself is always the same. The occurrence of the phenomenon changes in time, but what happens in the central engine remains more or less the same. We can infer masses of supermassive black holes that power quasars from their spectra and plot that as a function of redshift. Since the masses are correlated with luminosities, at high redshifts we only see the most massive ones. And here is an interesting plot that shows log of the mass of central engine versus redshift. At lower redshifts we probe to lower luminosities and there is a big spread. And as we go to high redshifts, we can only see high mass n. But what's really interesting is that even to the largest redshifts we probe, there are quasars powered by massive black holes that go up to 10 billion solar masses, which is remarkable. Assembling 10 billion solar masses in a volume smaller than a solar system is not an easy thing. And at redshift, say, 6 or thereabouts, you only had 1 billion years to do it. So that posed a little bit of a problem. How do you effectively make such massive black holes so quickly? We will talk a little more about this in the next module. Another interesting thing is that we can use the spectra of quasars to infer metallicities of the gas around them. And that, of course, is a product of a chemical evolution. The metals are being cooked up in stars, they explode as supernovae, and so on. And it turns out that even the most distant quasars known have very high abundances of heavy elements like carbon and oxygen and so on. This is also confirmed through detections of molecular gas around these high redshift quasars. And in fact, not only do they have these really massive black holes, but they also have metallicities exceeding solar metallicity. You can plot metallicity of quasars, or rather broadline regions around central engines, as a function of redshift, then you find that they can be even 10 times more metal-rich than Sun. Normally, this would require a lot of chemical evolution to happen. So what this means is in the cores of host galaxies of quasars, there was already a great deal of star formation and chemical enrichment history. And not only that, but those metals have been retained. They were not expelled by supernova-driven winds. So what this immediately implies is that quasars at very high redshifts occur in deep potential wells, and the places where we know such things can happen are cores of the most massive elliptical galaxies today. So that probably signifies that that's where they're originating. They're co-forming with the most massive galaxies. Somewhat more subtle effect is that the abundance patterns are slightly different. The abundances of heavy elements found depend on the type of supernovae. And you may remember that type 1 supernovae are detonating white dwarfs. Type 2 are really massive stars. And the abundance pattern for quasars is more characteristic of type 1 supernovae. And so that means that systems that give them rise, detonating, accreting white dwarfs, must have formed even earlier. So the star formation in these objects must have started at the largest redshift we can, higher than redshift of 10.